In 1895, a physicist named Wilhelm Röntgen was doing experiments with a cathode tube, a glass container in which a beam of electrons lights up a fluorescent window. He had wrapped cardboard around the tube to keep the fluorescent light from escaping when something peculiar happened. Another screen outside the tube was glowing. In other words, invisible rays had passed through the cardboard. Wilhelm had no idea what those rays were, so he called them X-rays. And the energy was emitted in the form of X-rays, which is a type of electromagnetic radiation with higher energy than visible light and lower energy than gamma rays.
Production of X-rays. The lab setup shown here was designed by Coolidge, and hence it is called Coolidge tube. It contains a highly evacuated glass bulb containing a cathode, which is a tungsten filament, and anode, which is a target made up of metal of high atomic weight. The pressure inside the bulb is maintained at 10 to the power of -6 millimeters mercury. When the cathode is heated by passing a current through it from a low-tension battery, it emits cathode rays. These rays are nothing but electrons. The filament is surrounded by a molybdenum cylinder, which is kept at a negative potential to the filament. This repels the electrons further, and hence the electrons form a fine pencil beam at the center of the cylinder. This pencil beam is also accelerated by the cylinder towards the target. The target is made up of a copper block in which a piece of tungsten or molybdenum is fixed. High thermal conductivity is used to carry away the heat generated to the cooling setup. Here we use copper, which is a good conductor of heat and can take the heat away from the molybdenum metal towards the water cooling system. The target is also tilted at an angle of 45 degrees, causing the electrons to hit at an angle. This will produce the X-rays almost perpendicular to the electron beam. A very high potential of 20 kV is applied between the source and the target. Due to the high potential difference, the electrons are accelerated towards the anode and it hits the metal. When it hits, the kinetic energy is transferred to produce X-rays. The intensity of the X-rays depends on the number of electrons striking the metal target. So, if we can increase the rate of electrons emitted by the filament by increasing the current flowing through the filament, then we can increase the intensity of the X-rays.
There are two ways to produce the X-ray. First is continuous X-ray, and second is characteristic X-ray. Continuous X-ray. It consists of radiations of all possible wavelengths from a certain lower limit to high value continuously, as in the case of visible light. X-rays are produced when high-velocity electrons strike the target material of high atomic number. The free electrons accelerate at high speed and kinetic energy and strike into the atomic nucleus. When they strike, the electrons decelerate at very high rate and lose some of its kinetic energy. Then the decelerating electrons radiate electromagnetic waves, which are called the X-rays. The rest of the kinetic energy is converted to heat, thus the anode will get hot. Next, we move to the characteristic X-ray. It is emitted from heavy elements when their electrons make transitions between the lower atomic energy levels. And electrons of high energy accelerate into the atomic nucleus, then knock orbital electrons in the K shell out of their orbits. The vacancy created will then filled by electrons from the L shell, producing wave called the characteristic X-rays.